Objective 2.9, Graphing Polynomial Functions. In this objective, we want to be able to determine the behavior of the graph at the x-intercepts and determine the end behavior of the graph. And then using those two pieces of information, we want to be able to sketch a reasonable graph of our polynomial function. So we already know how some simple polynomials look. We know that a linear polynomial like y equals x is just a straight line. We know that a quadratic polynomial like y equals x squared is going to be a U-shaped kind of line. But now we want to take a look at another simple graph that will help us with our more complex graphs. And this is the graph of our cubic polynomial y equals x cubed. So you can see here that we have a table of values with certain x values that I've chosen. And if we work out the corresponding y values, we would get this. So using our x and y coordinates to plot points, we would end up with a point here at -2, -8, here at -1, -1, then 0, 0, 1, 1, and 2, 8. And so when I graph a curve through these points, it's going to look something like this. So this is a new shape for us. We haven't seen this before. It's not a straight line that goes through. And it's also not just a U-shaped. It's what we call a shelf, because right here our graph kind of flattens out. And so we call that a shelf. Okay, so this is a new shape for us and one that we need to keep in mind as we start graphing more complicated polynomials. So here are our three forms for graphs, three shapes for graphs for some very basic polynomials. And what's nice is that these three shapes really work for any basic polynomial. Pretty much any y equal to x to an even power is going to look something like a quadratic. It's going to have that U shape to it. It's just that it's probably going to be a little wider than what the quadratic is. But that same general shape will hold for any x to an even power. Similarly, if I have x to an odd power, they're all going to have this same basic shelf shape to it. Again, it might be a little wider depending on what the exponent is, but the same basic shape will hold true. Okay, so what that tells us then is what's going to happen when we look at the end behavior of more complicated polynomials. Okay, so if you think about what's happening on the ends, we're talking about what's going on with the graph as x gets really, really large, or as it gets really, really small, meaning more and more negative. Okay, this is what we talk about when we talk about end behavior. So we're not interested in what's happening in the middle of the graph. We're just interested in where the ends are going. So if we have a graph of some polynomial, remember this is just the general form for a polynomial, this is how the end behavior works. If my a sub n is greater than 0 and n is even, then f of x approaches positive infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. Okay, now for the moment, just get these down, and then we're going to go back and kind of explain what they mean. So this is one possibility of what can happen with end behavior. Another possibility is that my a sub n is greater than 0, but my n is odd. In that case, f of x is going to approach negative infinity as x approaches negative infinity, and f of x is going to approach positive infinity as x approaches positive infinity. So that's a second possibility. A third possibility is that my a sub n is actually less than 0. And with an n that is even, then that's going to give me f of x going to negative infinity as x goes to negative infinity, and f of x going to negative infinity as x goes to positive infinity. And finally, the fourth possibility of what could happen with n behavior is if our a sub n is less than 0 and our n is odd. Then f of x would go to positive infinity as x goes to negative infinity, and f of x would go to negative infinity as x goes to positive infinity. Now that may seem really complicated when you read it that way, and that is sort of the mathematical way of describing what's happening on the ends, but it's not quite as complicated as it may look. So let's try to break it down into more common language. First of all, notice what we're talking about with a sub n and n. Again, a sub n here represents our leading coefficient. So every time they're talking about a sub n, they're talking about the leading coefficient. When is it positive? When is it negative? Okay? Then they're also talking about n. And if you look in our general form, n just represents the degree of our polynomial. So the biggest exponent, usually on the very first term, if we have it written in standard form, that's what we're referring to when we talk about n. So we're interested in when is n even and when is n odd. Okay? All right, so when we have positive leading coefficient and an even exponent, well, we just got done saying even exponents generally have a quadratic kind of shape in general. So even if I have a more complicated polynomial, the ends of my polynomial are still going to act the same way. And so when we have a positive leading coefficient, a positive a value, we know that quadratics have ends that both point up. And so in this case, having a positive leading coefficient and an even n for our degree, this is basically saying the same thing in just very mathematical terms. This is saying both ends are going to go up. Okay? And the way it's saying that is by saying f of x, which is the y values, are going to go to positive infinity. So they're going to go up as my x goes to negative infinity. So as my x moves me farther and farther to the left, my y's are going to be going farther and farther up. Okay, that's what the first part says. The second part says that f of x, which is again still y values, is going to also go to positive infinity, or up, as my x goes to positive infinity. So now we're saying on the right side, as x gets bigger and bigger to the positive side, going farther and farther to the right, then my graph is going to be going farther and farther up toward positive infinity. So this is saying my graph goes up as I go to the left, and this is saying my graph goes up as I move to the right. Okay? So with a leading coefficient that is positive and a degree that is negative, both ends go up. That's what that statement is actually saying. Okay, so if we continue that then, my next statement is saying if my leading coefficient is positive and my degree is odd, then it's going to act more like that cubic graph we just saw. So this part is saying that as my x's go to the left, my graph goes down. And this part is saying, as my x's go to the right, my graph goes up. Okay, so that's what happens in the cubic. That's what we just saw when we drew our new shape with the shelf. The left side was going down and the right side was going up. So a positive leading coefficient with an odd degree has end behavior that's going to act the same way. Now, if our leading coefficient ends up negative, then everything gets flipped around. So a negative leading coefficient with an even value is going to make both ends go down. That's why you see f of x going to negative infinity both times here. And if our leading coefficient is negative when our n is odd, then things flip. So now it's the left side that's going to go up and the right side that's going to go down, because the negative leading coefficient flips things around. Okay? So again, just think about what happens with the simple polynomials, and that will give you a clue as to what's going to happen with the end behavior of the more complicated polynomials. All right, so if we're just looking at end behavior, we want to be able to describe the end behavior of a graph of the polynomial by completing this statement. F of x goes where as x goes to negative infinity, so what's happening on the left side, and f of x goes where as x goes to positive infinity, what's happening on the right side. So in my first function, I need to identify my leading coefficient and my degree in order to decide what the end behavior is going to look like. So my leading coefficient is 1, and that's positive. My degree is 3, which is odd. And so for my end behavior, I would expect my left side to be going down to negative infinity, and my right side to be going up to positive infinity. Okay, so again, in just sort of common language, we're saying the left end is going down and the right end is going up when we write our end behavior with this notation. And that is how you need to write your description of end behavior, is using this notation. So start getting used to it, start practicing it. In my second example, if I identify my leading coefficient and my degree, I have a leading coefficient of -1 this time, so that's negative, and a degree of 8, which is going to be even. So this time, both of my ends are going to go down. So f of x is going to go to negative infinity on the left side, and f of x is going to go to negative infinity on the right side. Okay, why don't you give a couple a try? See if you can describe the end behavior of these two polynomial functions using the notation. Write it all out or fill it in. I can't remember what I put on your guided note sheet. But use the notation, describe the end behavior, and come back when you think you have your answers. All right, so in the first case we had a leading coefficient of -1 and a degree of 5. So a negative a sub n with an odd degree tells us that f of x is going to go to positive infinity as x goes to negative infinity, and f of x is going to go to negative infinity as x goes to positive infinity. So what we're saying is the left end goes up and the right end goes down. In the second example, we have a leading coefficient of 1, which is positive, and a degree of 4, which is even. So we're saying f of x will go to positive infinity as x goes to negative infinity, and f of x will go to positive infinity as x goes to positive infinity. So both ends will be going up. All right, so that's behavior on the ends of the graph. Now let's talk about the behavior of the graph at the x-intercepts. Sorry. So again, we can rely on our simple polynomials to help us with this also. It says the number of times a value is used as a zero in a function determines the behavior of the graph at that x-intercept. So if a number is used as a zero just once, then we would expect the behavior at the x-intercept to look linear. Okay, it's a linear factor. There's no exponent on it. There's no multiplicity to it other than 1. And so things should just look like a line, and our graph should just go straight through the x-axis at that particular x-intercept. If the number is being used as a zero twice, or really any even number of times, then we would expect the behavior to look like a quadratic, like a parabola. And so at the given zero, the graph would just touch the x-axis and then go back the way it came. So we're not actually going through the x-axis, we're just touching at that particular value. If the number is being used as a zero 3 times or any other odd number of times besides 1, then our behavior is going to look like our cubic function. And so that's when we're going to get that shelf kind of shape at the point that is our x-intercept. So we're going through the x-axis, but we're doing it in a little different way by using that shelf rather than just going straight through. So again, knowing the behavior of our simple polynomials can help us with what things are going to look like in our more complicated polynomials. All right, so let's put all of this together and see if we can graph this function. We're looking at f of x equals 3x cubed minus 4x squared minus 17x plus 6. Now this is a function from example 1 in the objective 2.7 lesson. So if you flip back to that, you'll see we already know what the factors of this polynomial are because we've already figured them out. And the factors ended up being x plus 2 times 3x minus 1 times x minus 3. Okay, so that means that the zeros of this polynomial are at negative 2, positive 1/3, and 3. Any real number 0 is the same as an x-intercept on the graph. That goes back to those 4 equivalent statements again. Okay, zeros and solutions are the same. Zeros and solutions can lead us to factors, and real number zeros can be seen as x-intercepts on the graph. So that means my zeros of negative 2, 1/3, and 3 are also going to be the x-intercepts on my graph. I can also find a y-intercept by putting 0 in for x and working it out. So in this case, that just leaves us with the constant of 6, and so that's another point that I know should be on my graph. So I'm going to go ahead and plot those 3 points as my zeros along with my y-intercept, and I'm starting to get an idea of what my graph might look like. Now I can also add to that the kind of behavior I'm expecting at the x-intercepts. Since each factor, and therefore each zero, only occurs once, we're going to expect the graph to just go straight through the x-axis at each of these x-intercepts. So again, when we start looking at our graph, we're expecting that things are just going to go straight through here, and straight through here. What we're not exactly sure of is which direction things are going to go, but we're starting to get an idea because we do know we have this point up here that we have to go through. But just to double check and make sure that we've got everything fitting together, let's talk about the end behavior. So at the end behavior, we have a 3 for our leading coefficient, which is positive. and a 3 for our degree, which is odd. So positive leading coefficient, odd degree, means that the left end is going to go down, so f of x goes to negative infinity as x goes to negative infinity, and the right end is going to go up. F of x goes to positive infinity as x goes to positive infinity. So knowing that my left end has to go down, my right end has to go up, and I have to go straight through each of these intercepts, I can now graph a pretty decent approximation of what my graph should look like. Maybe I want to go one more step and pick an x value in between these two x-intercepts, like maybe a 2, just to see whether it's a short little valley, whether it maybe comes down quite a bit farther. But in general, I can now graph this polynomial based on the fact that I have to go straight through at each of my x-intercepts. I have to go through this y-intercept as a point, and I have to make sure my graph ends up with end behavior that goes down on the left side and up on the right side. Okay, so there's the graph. All right, let's take a look at another one. Here we're looking at the function x to the fourth minus 2x cubed plus 10x squared minus 18x plus 9. Again, I've chosen a problem that we've already worked in a previous lesson, and so we already have the factors to this, which are x minus 1, and x squared plus 9. So that means we ended up with zeros of positive 1, 1 again, because it's a double factor, 3i, and negative 3i. Now, keep in mind that only the real number zeros will show up as x-intercepts on the graph. So our 3i and our negative 3i are not going to help us in terms of graphing. Only the 1 is going to help us. So that means I have an x-intercept at 1. I can also find my y-intercept, which should be at 9. And so I can plot those 2 points. There's my 1, and there's my 9. Now, if we talk about behavior at the x-intercept, since the 1 is used as a 0 twice, the graph will only touch at the x-intercept of 1. So it's going to act more like a quadratic because we use the 1 twice. And then for end behavior, if we take a look at our leading coefficient and our degree, we have a 1 for leading coefficient, which is positive, and a 4 for our degree, which is even. So we would expect both ends of our graph to be going up. All right, so let's put the pieces together here. I'm expecting this end to go up. I'm expecting this end to go up. And I'm expecting that intercept to have a touch. Now, I'm going to have to touch from the top because I also know that I have this point right here for my y-intercept that I need to go through. So there's no way I can touch from the bottom like this and then have a y-intercept up here. Okay, so I'm going to have to touch from the top, come down, touch my x-intercept, and then just head right back up. And if I want to be a little bit more precise, since I know a point on the left side of my x-intercept, I could also pick a point to the right. So I could pick an x value of 2, which gets me the point 13. And then I have everything I need to draw a decent graph. Okay. All right, so what if I give you the function already in factored form? So in the first two examples, I gave you a standard form function which you needed to factor, but since we'd already done that before, we kind of sped up that process. What if I give it to you in factored form in the first place? Well, we can easily tell then what our x-intercepts are. In this case, it will be 1 and -2. The y-intercept is a bit more tricky, but it's still the idea of putting 0 in for x. So if I put 0 in for x in the first factor, I get -1. If I put 0 in for x in the second factor, I'm going to get 2, which is then cubed. So the 8 from that factor times the -1 from the first factor will give me the -8. My behavior at the x-intercepts will be easy to tell now because I can tell from the exponents how many times each intercept gets used. So because my 1 is only being used as a 0 once, I expect the graph to go straight through at the x-intercept of 1. My -2, however, since it's in a factor that's being cubed, that means my -2 was used as a 0 3 times. And so I would expect my graph to do a shelf as it goes through the -2 x-intercept. And then for end behavior, this is the one that's a little trickier if you're already in standard form, but it's really not, or excuse me, already in factored form, but it's really not that difficult. Because if you think about it, my leading term is the result of taking this times this when it's cubed. Okay, so that really means my leading term in this case is just going to be x to the 4th. So leading coefficient in this case will just be a 1, which is positive, and then my degree is just going to be a 4, which is even. And what you can also do for degree is simply look at the exponents that you have here and add them up. If you're already in factored form, just add up all the exponents on your factors, and that will tell you the degree you would have in standard form. So, with a positive leading coefficient and an even degree, we would expect our ends to both go up. So, in the graph, there are my two x-intercepts. There's my y-intercept. Here's a couple more points to help me out and make sure that I'm getting a good graph. And I end up with a graph that looks something like this. Again, notice that we have more of a shelf happening here at the -2, and we're just going straight through here at the +1. Oops, sorry. All right, so it's your turn. Go ahead and give this one a try. Graph it out on the graph that's there on your paper, and then come back when you're ready to check. Make sure you go through all of the steps of identifying where are your x-intercepts, where are your y-intercepts, what kind of behavior do you expect at the x-intercepts, and what do you expect for end behavior. All right, so here are the results that you should have gotten. Our x-intercepts would be at 1 and -2. If we put 0 in for x, we should get a y-intercept of +2. We would expect our graph to touch the x-axis at 1 because that is being used as a 0 twice. And we would expect the graph to go straight through our x-axis at -2 because -2 is only being used once. And then we have a leading coefficient of 1 with a degree of 3, so we would expect our left end to go down and our right end to go up. Sorry. And so our graph should look something like that. And again, if you want to choose a couple of extra x values to make sure you're really getting good points, like the 2, 4 or the -1, 4, to give you an idea of just how big the bumps or the valleys might be, that's always a good idea. But this is what your graph should look like. All right, so you now have what you need to know to get through the problems in the Objective 2.9 practice. Make sure you work them out, find answers to your questions along the way, and don't forget to check your completed work on Canvas when you are finished. If you have any questions or issues, don't hesitate to email me. We'll see you next time.